Okay, so thank you very much for this invitation. I to be here with you. I assume I'm in this conference because of my long interest in physical computation and my previous work with Oron and Nir on physical computation and analog computation and stuff like that. And so thank you for this invitation to be here. But since my PhD, I have also a parallel long interest in the notion of algorithm and various formalizations of it. And so in this talk, I will be talking to you, I will be telling you about notions of algorithms and specifically with respect to geometric constructions. And something related to the Russian approach to constructions, to the so-called Russian constructivism. So let me start. So the motivating question is, the main question is, can we regard Euclidean constructions as algorithms? And if yes, in what sense? And why? First, let's see what do we mean by Euclidean constructions. A very classical, typical example, proposition from book one, first proposition in Euclid. Euclid tells us how to construct an equilateral triangle if we are given a segment, a specific segment, AD. So here are the steps of the, if you want to call it algorithm, or of the Euclidean construction. Start with the given segment. You draw a circle where one of the two extremes, one of the two ends of the segment will be the center of the circle. You draw the circle around it such that the circle passes through the other point. Then you draw the other circle, which center the other point, the other extremity of the given segment. And then you get the two intersection points of the circles. You choose one of the two, any of them, and then you draw the segments, these segments. You do this twice, and what you have there now is an equilateral triangle. So this was a very specific set of instructions, how to do it. So the question is this an algorithm, or in what sense of algorithm can we consider this as being algorithmic or not? And let's see also a very pre-theoretic idea of algorithm so that we are on the same page. So let's say that the classical algorithm, this is distinct from many computer science and logic textbooks. So let's say that in general, most people would agree it's something like that. An algorithm is a problem-solving process such that it is expressed as a set of instructions of finite size. It has a set of inputs, perhaps empty. It's carried out in discrete stepwise fashion. It proceeds in discrete time. It is in principle deterministic. I say in principle because not all algorithms are deterministic, but this is not specifically related to this talk. It describes steps that are easy and unambiguous. The idea is that an agent with very limited cognitive physical capacities is yet able to reach the solution. And it generally terminates after a finite number of steps. Some authors don't agree with that, but it's we can put it in brackets, and it's good for our purposes here. So, prima facie, geometric constructions, as the one I showed you before, fit well with this general idea. They are stepwise, composable, executable by rote. So many people have said that the Euclidean algorithm is the Euclidean construction satisfies all of the requirements of an algorithm. It is unambiguous, it's correct, it's terminated. We see claims like that in modern mathematicians, even in Kolmogorov, in his interpretation of intuitionistic logic. It's something that people keep saying a lot, that, yeah, the Euclidean construction is very good as an algorithm, why not? So in this talk, this is important. We will be concerned with the original idea of geometric constructions as it is in the elements, in the original Euclid, not modern reconstructions like Hilbert's geometry or other modern reconstructions. This means that since we will be faithful to the original Euclid, there's nothing, we won't have anything to do with real numbers there. We don't assume that any length corresponds, the points in one line in some segment corresponds one to one real numbers or anything like that. We don't assume a coordinated space. All these are later developments in geometry. Or use of real numbers to translate problems of geometry into algebraic ones and then prove results. Nothing of this is assumed here. We remain faithful to the original Euclid. And crucially, we don't also assume a pre-existing structure of entities, as we find in Hilbert. In Hilbert's formalization, we have some domain where the entities of this domain are, I don't know, points for Tarski or points and lines for Hilbert, everything, and then we can quantify over the entities of this domain and things like that. And specific relations. Nothing like that is found in the original Euclid. And rather the idea there is that Euclid gives us just constructions, in the sense that if you are given some initial entities, some initial objects, a segment, a point, a circle, then this is how you can proceed with the specific stipulated permitted constructions to generate the new objects. So the idea is more that we generate objects, final objects from input objects. We bring them into existence during the construction, if you want, in some sense. And these allowable constructions is those that are licensed by the stipulations we find in Euclidean geometry, which is mostly the definitions of a circle, of a segment, of a point, and the postulates. Let me remind you that the crucial ones are the first three postulates. The first one is that if you are given any two points, you can draw a segment between them. This is, let's say, the fundamental operation in constructions, one fundamental construction. For any 2 points, I'm able to draw a segment between the two. The other one is that if you have any segment, you can extend it continuously, as long as you want, until you meet some other line. And the third one is that given any 2 points, I'm always able to draw a circle, with one point being the center, and the other point will be on the circle. So what we saw that this was used in the previous construction. Right? These are, let's say, the primitive operations of the algorithms in quotes now. And of course, we focus exclusively on Euclidean plane geometry. So the question is, okay, are these constructions algorithms? We gave an idea of constructions. I gave an idea of what is an algorithm, but we need to make more precisely a notion of algorithm. Okay, what do you mean by algorithm? If you want to say that, if you want to examine if a construction is an algorithm, what exactly is an algorithm? The previous characterization I gave is not enough. So we do have sharper notions of algorithm. One is the classic, here I have the outline slide, but because I have to skip some slides because time is short, I will skip this slide. But the whole idea, what I'll be talking about this talk is that I will compare Euclidean constructions to let's say, the orthodox idea of algorithm, the one we know from the 30s, the 40s, the 50s, the classical idea of algorithm as a symbolic procedure, the one captured by Turing and the works of others, and then I will argue that Euclidean constructions cannot be seen, do not fit naturally with this idea of symbolic algorithms that we find in logic and computer science. Then I will introduce briefly another idea of algorithm that we find in mathematical practice. And then again, I will compare, if there is time, the idea of Euclidean construction to the other notion of algorithm, the abstract notion of algorithm that I will be calling. So first, the classical idea of algorithm. Well, most people in this audience are familiar with this. It's now almost history. So this is what I call the symbolic view of algorithms. It's a familiar one. It identifies the old idea of a problem-solving method. The idea that we find in the mathematical practice for centuries, if we open a book on the history of algorithms, we find there are methods that were devised in order to find solutions of mathematical problems, like bisection method, Newton's method, methods for solving systems of equations, things like that. Methods that now are the central subject of numerical analysis. And but then after the 30s, the developments of the 30s, where people for foundational reasons were sharpening the idea of an effective procedure through Church-Turing thesis and everything, we all know these stories. After that point, talk about algorithms somehow became inseparable from talk about effective computations. Algorithm became almost synonymous to effective computation. And just some historical examples. Turing does not speak about algorithms. He doesn't mention the term algorithm in his classical work, the 1936 work. We find it mentioned in Church as a synonymous to effective procedure, but people at the time were not defining the notion of algorithm. People in the 30s, they work in the 30s. But we find one of the first explicit statements about let's now define algorithms in the work of Markov and later in Kolmogorov and Uspensky, where they're trying to define a broader notion than Turing computation, which they call it algorithm, but it's always against the backdrop of the Church-Turing thesis. Algorithms considered in these works are always Turing computable algorithms. And a modern example, which still just one instance, one example where we see this identification between the idea of an algorithm and an idea and the notion of an effective procedure, and then its formalizations as Turing machine or whatever, is here. There is Papadimitriou. We therefore propose to adopt the Turing machine that halts on all inputs as the precise formal notion corresponding to the intuitive notion of an algorithm. Nothing will be considered an algorithm if it cannot be rendered as a Turing machine, and all such machines will be rightfully called algorithms. You find this all over the place in computer science textbooks, logic textbooks, Di Freddi, anywhere. Like I have dozens of examples, quotes like this. And as Dean notes, now sections like this have become stable in computability and complexity theory, that there is no algorithm that decides the validity of any first-order sentence. This is the decision problem, Hilbert's decision problem, or that there is no algorithm that solves the Boolean satisfiability problem in polynomial time. Okay, and since these first formal methods developed to explore computability were symbolic ones, we had machine models, symbolic models at the time, post-Turing and everything, and algorithms were their computations were regarded as symbol manipulations. We see this as a motto almost everywhere. Then algorithms, since algorithms were identified with effective procedures, algorithms were also understood symbolically. So in this, we find this in many works. Again, Markov considers only algorithms in given alphabets, operating with concrete words. Kolmogorov and Uspensky, the definition of algorithm, say that without fixing a standard way of writing numbers, to speak of the algorithm computing would make no sense. First, we have to fix a standard way of writing numbers. And Shapiro, in this article that he mentioned in his talk 2 days ago, he expresses the same sentiment. Mechanical devices engaged in computation and humans following algorithms do not encounter numbers themselves, but rather physical objects, such as ink marked on paper. Since strings are the relevant abstract forms of these physical objects, algorithms should be understood as procedures for the manipulation of strings. So the idea here in general is that give me your alphabet, give me the symbols, the notational symbolic system you're going to be using, and then I will give you the algorithm, because it will be sensitive to the exact way we represent things, to the exact alphabet. I change the alphabet, the sequence of steps changes, we have a different algorithm then. So the identity conditions of these algorithms are dependent on the chosen representations and symbolic and symbols and everything. So on this idea, symbolic algorithms operate on strings of symbols, either words, numerals, strokes, whatever, decimal numbers, what we learn when we learn multiplication at school, binary numbers, what have you. And one can consider these objects that the algorithms operate upon as quasi-concrete in the sense of Parsons. Parsons introduces this idea of quasi-concrete objects, where some abstract objects are distinguished by the fact that they have an intrinsic relation to the concrete. They are determined by their concrete embodiments. What makes an object quasi-concrete is that it is of a kind which goes with an intrinsic concrete representation, such that different objects of the kind in question are distinguishable by having different representations. So the crucial idea again here is that, but the crucial idea again is that we don't compute, these algorithms do not operate over the abstract entities, numbers, what have you, but we compute over the adopted names or descriptions of representations of the mathematical entities. It's always the name there, the representation I have in front of me, the string of letters that I manipulate. And these names descriptions possess some properties of their own that are not necessarily properties of the number itself. Like a decimal system is positional. A Roman numerical system is not positional, for example. Or we talk about the string the length of a string. These are properties of the representation. They're not properties of the abstract numbers themselves. But these are properties that we exploit during the computation. And some more restrictions are that these names are also comprised of atomic, indivisible parts, such that the type remains unchanged during the computation, not the reference. Think again, all this time you can think either as stroke numerals or decimal numerals or what have you. The thing is that the decimal numerals are atomic. I can move them around, but they are indivisible. I do not break the numeral 5 into pieces. I just combinatorially manipulate it as it is. It's atomic, it's indivisible. And they allow forming composites in ways that reflect our epistemic picture of the structure under consideration. This is what Kripke calls structural revelatory, that the good representations, the appropriate representations, are those that somehow reveal the structure I have in mind. The structure, the stroke numerals are good because, as Stuart told us, argued 3 days ago, somehow represent fundamental properties of the structure of the natural numbers. They have the successor operation and all these things. Sometimes stronger requirements have been proposed for acceptable notations. There's a big debate there, which Paula knows very, very well. She's an expert on these issues. So Stuart, 40 years ago, required, and he reminded us about this today, is that he requires that the successor function be computable in the notation. Rescorla asks for that the notations have computable semantics. Jack and Diane Proudfoot take as acceptable inputs to Turing machines those that can be outputted by a Turing machine with no input. Stuart now gave an extra criterion in this talk with his co-authors that they examine notations that satisfy the role of number expressions in ordinary context, and the list keeps expanding. Now, new criteria are formulated all the time. All these are extremely interesting. This debate is this discussion is ongoing, it's extremely interesting. But we are going to focus here from the point of view of the Rossian constructivist approach, how they dealt with the problem. What exactly are the requirements for a good notational system so that we can use it for accurate computations? And on these views, the objects that we operate upon, that algorithms, symbolic algorithms operate upon, are considered constructive objects. And this is the key notion of this talk, the key idea. My shadow blocks the letters, I guess, sometimes. I should take care of this. Problem solved. So here is Kolmogorov, cited by Uspensky and Smenov. Any natural number can be given constructively as this. 1 + 1 + 1. Here we see the difference between a natural number as a quantitative entity, which is not a constructive object, the number 6, what have you, and its representation as a sequence of signs, which is a constructive object, actually. Then Martin Lev says that all objects we shall consider are to be constructive objects, which mean finite configurations of signs. These signs can be immediately be recognized as being equal or different, and are treated as atoms that cannot be further decomposed. And for Martin Lev, this is exactly what Post and Turing is about constructive objects. Okay. There's an issue.
Something about the camera is not working.
I'm not visible.
I'll go and check.
Anyway, they don't miss anything if they don't see me. So constructive objects in this tradition have a twofold use. They are either the primary objects of studying constructive mathematics, or the object operated upon by symbolic algorithms. And let's keep this. But it's the central idea in the constructive approach to mathematics and to computation, because these are almost very close. Like for Markov, constructive mathematics are just computational mathematics in a sense. And as Kushner, this student of Markov, says, Markov placed a special accent on the syntactic character of his system. Constructive objects and constructive processes are the main and essentially the only dramatis persona on the scene. Constructive objects are considered to be initial data for algorithms. Nagorny in the Soviet Encyclopedia of Mathematics says a name used for mathematical objects that arise as a result of completing so-called constructive processes. This is what a constructive object is. And Uspensky says algorithms may deal only with constructive objects. This is all quotes that you can find from Russians, because it's very difficult to find Russian text translated into English. And there's a treasure there of ideas. And this is unfortunate that it's so difficult to locate any piece that is written in English or translated in English. But what exactly is constructive object in a little more detail, and we need this because we're going to compare constructive objects to Euclidean diagrams and Euclidean constructions. This is the core of the argument. So this is why I'm insisting on these details about the constructive object. So we find the best attempt to a specific characterization in Uspensky and Semenov. We assume that any constructive object contains a finite set of elements. So first of all, constructive objects are finite. But not every finite collection is a constructive object. We need something more. Each of these elements in this finite collection, which we will consider a constructive object, belongs to one of a finite number of types. Okay, for example, the word elephant contains 8 letters of 7 different types. The elements are connected by some relations. A constructive object has a discrete structure and contains separate elements, just as a molecule contains atoms. We assume that for a constructive object, an internal coordinate system, this is very interesting, is given. Not maybe given, but already given, which can be used to identify uniquely any of the elements. This is the key ingredient. And for a coordinate system, it is natural to have an origin. So for any constructive object, one of its elements is chosen as an initial element. Here are some examples. Words in alphabets are constructive. Because we can always consider the first element as the starting point, the initial element. And then we have a coordinate system in the sense I can always tell you, if you know nothing about this, go to the 5th element, go to the 7th. So I give you anything you need. There is only one linear order relation. I give you anything you need to go to a specific element and do what you have to do while executing the algorithm. Matrices. They have an internal coordinate system, actually, because we talk about elements and rows. So I can tell you here is the starting point. This is actually how we use them. Go to the element in the 5th row, 3rd column. So it's already implicit coordinate system somehow. And rooted trees, not any kind of trees, but rooted trees, because we have an initial element, the root. So then I have all the details here necessary to guide you to any specific element. Here are some examples of non-constructive objects, because they are symmetrical. There's no way, there's no initial starting point, initial element. They are somehow indiscernible from this point of view. Cycle graphs, for example, or finite collections in general without a coordinate system. So the crucial requirements are to be able to specify all relations between the various elements, and then to have an initial element so that the computer can navigate mechanically within the constructive object starting from the initial element. The computer is always assumed to have no clue, absolutely dumb, knows nothing, so we have to give very precise details, go to this part, go to the other part. An example is that you may have a detailed map of a city. Here, all the relations are specified in the map, but if you don't know where you are in the map is useless. So you need both requirements, actually. And constructive objects serve also very nicely to make the locality idea behind computation more specific. But let's not focus on locality here. And here I have a pictorial analogy, because I guess a reason we all love Lego is that always the instructions of Lego games were very clear, right? Here is a constructive object representation because we have all the relations, we have an initial object. And we have local operations in the instructions of Lego. Always they start from an initial point, and then locally it tells you how to add pieces. But I'm sure that many of us have struggled with assembly instructions like this, where this is not a constructive, definitely it's not a constructive object representation. It just tells you everything fits this way, there's no initial element, there's nothing. And then you struggle to follow the steps, because I'm sure everyone has had trouble with this in the past, where you are given this not locally, but globally, like here is how everything fits with each other. Now go figure out yourself how to start assembling this. Sometimes we start from a wrong piece and we say, oh, I assembled this first, I should have started from the other one. So this is definitely not constructive. So a finite object can have more than one constructive object representation. And but what is important is that any kind of constructive object representation can be turned into some word. There is a way to do this. Zig has showed this. Martin Lev, Kolmogorov, and Uspensky, they show that here are ways to encode everything in a constructive object where the only relation that matters is linear order. Here we may have more than one relation, but it's always translatable to a word. So if assuming that the two requirements of having an initial element and all the relations specified are known. So to summarize this idea of algorithms, their existence and identity is always contingent on the symbolic representations. You change the symbolic representation, the sequence of steps change, the algorithm changes, because the algorithm is very sensitive on the specific detailed sequences of steps. They operate on constructive objects. The primitive operations are always finite. They can be identified with concrete computations. Okay, this is not important for this talk. And they're always effective, as we know, via church unit thesis, or if we're talking about real numbers, via a counterpart of the uncountable church unit thesis. But they're always Turing computable. They are effective. Now, can we see constructions like this as instances of these processes? The answer is negative. Similarly to these are the reasons, similarly to canonical representations of numbers. First, the similarities. A Euclidean diagram can also prima facie be seen as a kind of symbolic representation, the diagram itself. Consisted of elementary symbols, points, segments, lines, okay? So you can think that the circle is an elementary symbol, here is another symbol. So in a sense, they are symbolic. And we use them to create composites, triangle squares. And also these objects can naturally be considered as quasi-concrete in the sense of Parsons, right? They are very tightly connected to how you represent them. The abstract objects rely on how you represent them very much. But despite this superficial similarity, there are fundamental differences which have to do with the representation system itself, the symbolic system itself, and the properties of the configurations. Let's go into that. So some of the differences, the representations used in symbolic algorithms, as we said, comprise atomic indivisible symbols that remain as they are, as such during the whole process. I'm manipulating, but the number 5, the numeral 5, the digit 5 remains always a 5. But this is not the case with Euclidean diagrams, because here representations are not necessarily taken as atomic. And triangle can either be treated as one entity, but it can also be decomposed in 3 segments. So we have 3 new entities. This is not the case with the number 5, right? We do not break it into 2 parts of the number 5. A segment can be extended, and its 2 extremities are distinct entities. So this is fundamental difference. They are not atomic. We don't have atomic parts there, except maybe the point. Numbers and other objects of symbolic computations can be canonically represented as constructive objects in more than one way, as we said. You can represent a number as a stroke notation, binary, decimal, what have you. But there is a unique canonical representation of the Euclidean objects, which is licensed by the stipulation, by Euclid's stipulations, the definitions and the postulates. Since he gives a definition of a segment, so there's only one way to canonically represent the segment, or he gives a definition of a circle. So you have only one way to represent it. Let's skip this now for the interest of time. And in symbolic computations, the atomic symbols are combinatorially operated upon. I move them around, manipulate them based on their types. We don't cross them, we don't juxtapose them. And computed entities are only those affected by the combinations according to the primitive operations. This is not the case with Euclidean diagrams, where first the symbols can intersect, can be juxtaposed, all these things that are not allowed in symbolic algorithms. And also, such actions can result in the creation of new entities, like byproducts. We have the generation of new entities as byproduct of the instructions of the primitive operations. This is key, actually, for Euclid. Which are not licensed by the constitutive stipulations. And here is the very classical example, that when Euclid gives this construction, he presupposes that the intersection point between the two circles exists, that there is a point here that I can choose. This is not licensed by the postulates and the definitions of original Euclid, because he assumes there a continuity, that the circle is continuous. Nothing of this is part of the primitive operations of the stipulated operations. He gets this from the diagram, according to many interpreters. It's the diagram which is continuous, and I take this property of the symbolic representation, and I transfer it to the abstract object, and I infer that also the abstract circle itself is continuous, and so there is intersection point. But nothing of the sort happens with algorithms, right? There's no way that some of the properties of the representation, like the length of a string or whatever, will allow you to transfer new properties for the numbers themselves that you didn't have before, that you get them from the representation. And yes. And the most important, another one is that constructive objects, as we said, are closely connected with the idea of local operations. But in diagrams, some of the stipulated operations are not local, like most notably the one postulate 2, which says to produce a limited, if you have a limited segment, you can always produce it, extend it continuously until you reach a desired point. This is not local. This is actually global. In a sense, somehow it requires a global inspection of the agent to know that there is a line waiting, so I can do it, or an unbounded operation in a sense. But the most important and interesting case is that by conception, the constructive object is equipped with some kind of internal coordinate system, so that the computing agent, by following the instruction of the algorithm, as we said, can navigate mechanically through the elements of the configuration, as we said. Crucially, this is not the case with Euclidean diagrams. They cannot be seen as constructive objects with such properties. Euclidean diagrams do not provide a bona fide way of distinguishing between elements of the same time or between variant configurations. Let's see examples. In a sense, the Euclidean diagram indetermines the mathematical state of affairs, and I will explain in what sense. But there is some kind of, I'm not sure if it's under determination of indeterminacy, but it is one of the two of the actual mathematical state of affairs, let's say, and what you see in front of you in the Euclidean diagram. I will explain now. For example, if you have a triangle, right? Just imagine a triangle. There is no way to descend between the vertices from an intrinsic point of view. Which one is which? It's just symmetrical. I may put labels A, B, C, but if you are inside, let's say, in the constructive object, in the Euclidean diagram, you cannot distinguish between the 3 points. They're indiscernible. I'll give a better example that will make it even clearer. But the idea is that the workspace is completely homogeneous. And the Euclidean diagram does not provide the necessary relations to completely pin down the current configuration. In a sense, this is what we said before, that cycle graphs is not a constructive object, right? Because this is, in a sense, these are indiscernible from a mathematical point of view. I cannot tell you, like, if you are here, how can I tell you go there or there, if or if there is no initial element? I'll give a better example. This is a more clear example. I think it will clarify what we mean. Consider these following 3 cases, right? For us, we understand them as different states of affairs, different configurations. But they are not so from a constructive point of view. There is no way to distinguish them. Let's say that we somehow try to write down a formula which captures in some language, some appropriate language, all the relations that are licensed by Euclid, by Euclidean geometry. All the relations that are fundamental there are fundamentally used by Euclid in his proofs. The relation of being inside the circle or outside of circle is something that Euclid uses a lot. So if here my collaborator Alberto Naibo, this talk is trying to work with him, but also Marco Panza and 2 other authors have tried, this is work in progress, they're trying to formalize all the relations and everything that is licensed by the original Euclid. So let's accept for this talk, but this is a formula in an appropriate language that captures what's going on here. So we see that Euclid these are Euclidean judgments, they are called Euclidean judgments. So we here have the relation that we have a circle alpha, which has the alpha A as the center and crosses B on the circle. Then alpha is the point A is inside the circle, the point B is on the circle. We have a segment between C and D, the point C and D. The point C is inside the circle, the point D is outside the circle, blah, 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 and the other two. The thing is that the same formula is consistent with all 3. There is no way to tell between these 3 states of affairs. There's no way to tell at the constructive level. They're just indiscernible, but they are different. And why they're different? Because if I make a further construction allowed by Euclid, then I can tell. So if I draw the segment AB, then these two become different. Because if I draw the diameter AB, then I can distinguish between these 2 segments, which is not the case actually between these 2. So they are different mathematically, but we need further constructions to see this. Okay, so the idea then is that the argument here is that constructive Euclidean constructions do not fit naturally with the idea of algorithms as symbolic procedures, but still there is some strong intuition, as we said, that there is something algorithmic in them. There is something that conforms to this pre-theoretic idea, complies with this pre-theoretic idea. What is it? Does it mean that all these intuitions are not necessarily? But now I have very short time. And so very briefly, some people in this audience were in Dubrovnik when they listened to me arguing that there is another notion of algorithm, which is found a parallel conceptualization of algorithms, which we find in mathematical practice. This conception has to do with algorithms as abstract array procedures. I gave a detailed talk and arguments about the second view, the controversial suggestion in Dubrovnik. Now I will need a second talk inside this talk. Do you allow me to do this? Or? So anyway, briefly, just Except that maybe there are some arguments that there is a second parallel idea of abstract algorithms, right? And if you are doubtful, there is an upcoming paper, it should be out very soon in Philosophia Mathematica, where I give all the arguments why we have a second idea of algorithms, which is not symbolic at all. And it's better to understand it as having to do with processes over abstract entities directly, not mediated by representations. And these algorithms are not effective. They come from the tradition of problem-solving stratagems in mathematics. There is no concern with any rigorous idea of effectivity. Actually, they are not effective, most of them, like if in numerical analysis. Many algorithms like Newton's method, dissection method, are not effective because they involve essentially and fundamentally non-effective operations, such as comparisons between real numbers. And I have all the arguments that I should rush. Anyway, this is the example of bisection method of one such algorithm, which not only it's not effective because it essentially involves at some step comparing two reals and then deciding which real is the order between the two reals and then continuing. And these are not, it seems a stretch to conceptualize these methods as symbolic manipulations. On the other hand, you open a textbook in numerical analysis and all practitioners there say, oh, this subject is algorithms. The whole idea is to develop algorithms, which are not computable from an analytic point of view, but they're still, they exactly conform to the idea of an algorithm. And these methods, if you accept now the arguments that I haven't given you, but I haven't maybe for the Q&A, if you accept that there is this parallel idea of algorithms which are operating on the array objects, these algorithms, the identity conditions of these algorithms are not dependent on the choice of symbolic representation, on the choice of the symbols of the notational systems. They have an identity natural structure of their own, and this is reflected in our practice of giving proper names to them. We talk about Euclid's algorithm, Newton's algorithm, Gauss elimination, which are independent whether you decide to represent numbers in real numbers in stroke notation or binary or decimal or whatever, not stroke, binary notation, decimal, Cauchy sequences or whatever. And there are also some other properties that we assign to these algorithms that cannot make sense if you see algorithms as symbolic procedures. These are properties that do not make sense of if you understand these algorithms as operating over the real numbers themselves. Unfortunately, I don't have time to give more details for these arguments. But I mentioned it here because then it could be the case that we could see geometric constructions as conforming to this idea of algorithms. And what I say here is that they describe the array procedures. What I mean the array. So there is this distinction between the array Dichter that Quine came up with, coming from Russell initially. In the mathematical context, would look like this. We have this equation, right? This function. Alice knows. We have this statement. Alice knows that that this equation has a double root. This has two readings, a Dichter and a array reading. And the Dichter reading is that Alice knows that there exists some number which is the double root of the equation. The array reading is that there exists a specific number, Alice knows this number, pi in this case, which knows of pi that it is the double root. This is the array knowledge. So the idea is that these algorithms are meant as if operating directly, not on the names and the descriptions, but directly over the abstract entities. Let's skip these, although this is a good point, but okay, I will also skip this, but these are in case of some objections. I'm sure there are many. But anyway, the two ideas here of algorithms is that the first, as we said, the existing identity is contingent on the symbolic representation, blah, 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 we said all this. The other notion of algorithm is that the existence is relative to some implicit model or level. So give me your model of operation, tell me what are the primitive operations, and then I'll give you the algorithm. But it depends on any kind of stipulated operations, and these stipulated primitive operations could be infinite, such as comparing two real numbers. And could geometrical constructions be seen as this? Not really. Again, there are more similarities of Euclidean constructions to the abstract idea of algorithms as we find it in numerical analysis and other mathematical areas. There are similarities, but there are also differences. The similarities is that there is no concern with effectivity or Turing computability. This is an orthogonal case, both for numerical algorithms and for geometric constructions. And they are both, in both cases, we have these algorithms are conceptually closer to a model level relative conception, right? Give me the permitted operations, and then I give you the sequence of steps. Okay, just the difference then. But the difference, the main difference is that in numerical algorithms, we presuppose that there is a structure of real numbers there. That's what I mean there. So they are meant as if we presuppose all the real numbers. And then I start from the inputs, and I give an algorithm that gives me the outputs, let's say the solution of the equation. But we cannot do this in geometrical constructions because we said that there is no pre-existing domain. We generate the objects during the construction. So in that sense, they cannot be seen as direct. And because also that there are no indiscernible. Many objects there are not indiscernible, as we said, until we perform some further constructions. Now, I only say this because this replies to something from Stewart's paper. So I need only half a minute to say how this connects to Stewart's paper. So Stewart's, in the paper that he presented 2 days ago with his co-authors, he says in the end that we cannot have direct knowledge of geometrical objects in Euclidean geometry because the space is homogeneous. But then, if we reach the point at which after some specific constructions, we have descendability, we can descend the different state of affairs, as I showed in that example, then the results of the constructions can become known there. Then we know there. And in this case, there is not even the need. No, the other one is the thank you slide. So it's one line. And in this case, there's not even need for some privilege notations that work vividly. So in the case, there's all this debate about privilege notations in symbolic algorithms over numbers, which is privilege stroke, decimal, binary, many arguments there. But in this case, this question doesn't arise. And there, in the other argument, we talk about backstopping notations coming from Kripke, which are privileged somehow. But here, this doesn't even arise because we have only a unique representation in Euclidean geometry, and the constructions refer simultaneously to the diagram, as Marco Panza argues, and it's a very nice argument, to the diagram and the abstract object itself. So somehow there's already one, and this is privilege notation and backstopping notation at the same time, after we have the knowledge, and that was it. Okay.
Yeah. This isn't really a question, it's just a quick observation in case relevant. It's something that Bernard said, and I guess my interest is the connection between what you're saying and decision problems. And Bernard's Erwin Engeler told me that Bernard's would often say that the first appearance of an Entscheidungsverfahren, a decision method in the work of the Hilbert School, was in the geometrical work by Hilbert that you were referring to.
The first appearance of the decision problem?
Of a decision procedure was a Euclidean process. So that,
But that's in the Hilbert's geometry, where things are very different.
well, can you say a bit more about that?
About how it's different?
Yes.
There are not the Euclidean gaps. I mean, Hilbert lays out all the necessary constructions, but they're not really constructions. They are mostly existence statements, like that there exist points, then there exists the line, or for any line there exist points that the incidence axioms there. So for Hilbert, there is a domain already of entities. Then his axiomatic approach somehow captures, gives the actions that capture the relations in the existing domain. And you can quantify and you can say things like that. And you can do, but this doesn't exist in Euclid at all. There's no pre-existing domain. There's no, you generate the objects during the construction. You cannot quantify. It doesn't make sense to quantify if you don't have all the entities already there. And so I don't know what the decision problem in that sense of Hilbert's would look like in Euclidean geometry. What was the Hilbert's? What was the decision problem that can be found in Hilbert's?
Oh, I can email you both
Okay, great, thanks.
Right. Yeah, at the end, I was not sure why you separated the geometric algorithms or constructions from the numerical analysis. Yeah, I mean, the representation. Well, maybe it went too quickly at the end, but at some point I lost you. I mean, you have the representations, right? That can be, words or versus diagrams, for instance, right? And then there is what they describe, right? And in the case of the geometric diagrams, so probably they describe some segments, right? Or things like this. And in the case of let's say Turing machines, right? What do you describe is like set of strings or things like this that are themselves representations, right? So I wasn't sure at the end when you talk about geometry, where you put the focus on the diagrams or what the diagrams represent. What?
But of course, it's not a straightforward issue in Euclid to understand, right? There's lots of literature in that.
Yeah, but for you, I wasn't sure at the end what was the focus of the difference.
Of the difference.
Yeah, between geometric and what you call
Abstract.
geometrical algorithms and symbolic.
Symbolic.
Yeah, let's see. With the numerical, I completely yeah, and the symbolic. Yeah, let's start with the symbolic.
So they don't open Euclidean. In Euclidean geometry, you're dealing with the diagram necessarily. And the diagram is necessary because it assigns properties to the abstract entities, like the continuity. You need the diagram, and from the diagram, you infer things that are necessary for the construction that are not part of the abstract domain, let's say, like that the circle is continuous. This Euclid infers it implicitly from the diagram, or at least according to some interpreters, and I agree. It's not in the actions. It's not anywhere. It's not in Euclid's postulates. So somehow he fills the gap, inferring from the diagram, but because the diagram, the physical diagram is continuous, when I draw the circle, there is an intersection point between the circle and a line and another. So somehow he infers the continuity property from the diagram itself, and he transfers this property there. So in that case, the diagram transfer properties. We infer properties about the mathematical domain from the diagram itself, which doesn't happen in symbolic.
Not only is symbolic, I mean, when I studied geometry in high school, we
That's
were
very
told explicitly not to do that.
Not to do what? Not to infer. Yeah, I know.
From the diagram.
I know. Yeah, of course. I know. It's very difficult to switch your mind to this idea because I taught also geometry in high school and I always believed these things. And then Alberto was like, no, it's totally different. And then it took time to convince me, but it's exactly the opposite, actually. The original Euclid. What we learn at school is something more modern. So one thing is this: the Euclidean diagram is not constructive for the reasons I said. I mean, you don't, in a constructive object, everything is specified with this internal coordinate system. But in the Euclidean diagram, there is indeterminacy, and then you do a further construction, and maybe you remove the indeterminacy. You remember this diagram I said with three cases that are consistent with the same formal description. So they are far from constructive. If you are, or not if you, but if I have a dumb computer in front of me, I cannot tell them mechanically, do this, go to this point, find the point that is outside of the circle, draw the line between the one point that is outside of the circle and the other point that is inside the circle. I cannot have ways to constructively describe these things in a Euclidean diagram. Somehow, it's us, the humans with cognitive capabilities, that we see the whole diagram, and we say, okay, I know between which points you want me to draw the line. But constructively, for a computer, so again, all this is because we presuppose that there is no coordinate space. If you presuppose a system of coordinates, everything is solved. That's why now we have computational geometry is everything. But the point is that this doesn't exist in Euclid. Nothing like that. Real numbers behind coordinate space and things like that. I mean, if we have coordinate space, then of course every point is represented as a pair, ordered pair, and then we manipulate the pairs themselves. We have algebraic solutions, but these are different algorithms. I mean, if you have a coordinate space and you translate everything to algebraic equations, and then you manipulate the algebraic equations, as we learned also in high school, the equation of the line, the equation of a circle. It's a totally different algorithm. It's not a Euclidean construction anymore. This is a symbolic algorithm. And they're not even effective sometimes. I mean, it's an orthogonal issue whether they're effective. They're not local. Sometimes you need to know from the diagram that you can extend it until you will meet something. You don't know if there is another line. Like you extend this line until you meet the circle, let's say. You don't know it is local, right? You have to see the whole diagram to understand. So
Okay.
roughly these.
Sorry to interrupt, but we do need to end the session. So thank you.
Thank you.
our speaker. All right. Without further ado, Carl Posey will give us a dilemma for determinism.
Thank you. And as the last speaker, it's my great pleasure to thank the organizers for, I have to stand out of that light because it's in my eyes. To thank the organizers for putting together this wonderful, wonderful conference. I in particular want to thank Oron, though. Anyone familiar with his book will know how much this talk is indebted to it. Anything good in the talk, that is. Actually, the whole conference, as we've seen. But my own special debt is that what I'm going to say now actually stems from a conversation and a correspondence that Oron and I had in November of 2020, just before his book began, just before his book came out. And I promised him that I would think further about some of the things in that conversation. And Oron, here it is.
Okay, this is the only reason that we have the conference to make you.
As I said, I find myself in those of you who know baseball, the cleanup position. I'm resting on summarizing, addressing much that has gone before with this conference, in this conference. And I have to say that I'm doing it with a certain amount of trepidation. I'm not among the players in this discussion. And so I view what's gone on here from the outside to a certain extent and from a distance. But because of the distance, actually, I'm going to look at what we've done from a bird's eye point of view and look at it in really very general structural terms. And some parts perhaps a little outre, they'll be explained though, and put it in some historical context. Our task as philosophers of computation is to find the notion of computability of physical systems, or so that at least the generally accepted systems, laptops, desktops, brains, count as computing, and the obvious non-computers, stomachs, solar systems, a rock, do not count as computers. I brought two computers here today. In this talk, I'm going to distinguish two approaches to giving that definition of physical computability, or physical computation, what I call the extrinsic approach, implementation in one form or another, and an intrinsic approach, appealing to the architecture or ultimately mechanistic description of the machine that is supposed to be computing. The extrinsic approaches come with two sorts of indeterminacy. What I call a pernicious indeterminacy and a benign, following Jack, even useful, beneficial indeterminacy. The definers of computability, some of whom are sitting in this room and have sat in this room, have labored mightily to devise extrinsic accounts of computability without the pernicious indeterminacy. But I'm going to suggest that it's unavoidable. That, or more precisely, that if you embrace the benign indeterminacy, then the pernicious cousin comes along for the ride. That's one horn of the dilemma about which I'm going to speak. The other is that the alternative intrinsic accounts of physical computability are ultimately too weak, they let in too much. And when we strengthen them, they simply slip back into the extrinsic mode. So the dilemma is extrinsic with bad indeterminacy or intrinsic with too weak, no real grounding. I'll set that out for you in general terms. Okay, but having set up the dilemma, I'll do it with a little bit of detail in a couple of examples, and then wave my hands at what else can be done in order to, just get the general idea. But having set up the dilemma, I will take a stab at how we might avoid this conundrum. I'll point out that this avoidance, though, I'll put the conundrum in a somewhat historical perspective, and then point out, though, that the avoidance comes with a cost in practice, a certain discipline that needs to be adopted. I'll close with some more general, very general, very speculative metaphysical remarks. I say I'm taking a stab at a solution. I'm telling you now that it is indeed a stab, a general idea, and something that I will propose is worth thinking about and working on. Okay, so let's get started. And let's move to the extrinsic accounts of indeterminacy. Extrinsic accounts say in one form or another that the physical system in question is a version of a recognized computing system. By version, we generally interpret that as a realization or an implementation. Okay. In general, we start with some paradigm instance of a system. I'll call it S for the source, that is computing an ideal automaton, or in some languages, just a formalism, that, as we know, has states. States are information states in the most intuitive cases. Perhaps we factor in input and output. And in the course of a computation, it transitions from one state to another. Then we say that a given physical system, T for the target, implements that ideal system S if there is a one-to-one mapping, a homomorphism, H, from the states in S to components of T, and from the transitions in S to the transitions in T, that preserve the arrangement of those transitions. S is the source, T is the target. Okay, that's the sort of thing that we are looking for. And here's a simple example. The source has two states. The target may often have more states, but actually only two of those occur in a particular slice of time where this is doing its actions. Here are the state transitions in the source, and this can be said to be implementing the source when we have this correspondence between the transitions in the source and the transitions in the target. Nothing that you haven't heard at least 25 times in this in this conference. Let me give you a more precise definition of this. So in general, we can do this even with a picture. In general, the source will have some states, and it will move from one state to the next, which I've renamed S for S states. These are just various ones of the P's, and this is designed in order to have the notation represent the order. Okay, and so each of these S's is one of the P's, but it could come up more than once, and so it might get different S indices, and we do the same thing on the target side. And once again, there has to be a homomorphism, a one-to-one mapping from the appropriate number, the states that actually figure into the transition and states of the target, so that the target's transition matches the source's transition. Okay, that's just a general statement of what it means to implement in the most broad terms. Okay, as I said, certainly recognized computing machines, desktops, laptops, and with the appropriate work that people here know how to do much better than I do, brains fit this model of implementation. And so we want to say that this is what we're aiming to generalize. We want it to be that when we have a relation like this between a source and a putative target, then insofar as the target fits into this relation to the source, we say that it is implementing the algorithm or the formalism, whatever the source might be, and it counts as computed. Okay, that's the picture that we'd like to get. But it's a picture, as we've seen several times, comes with a devious, pernicious, undermining argument. Okay, the triviality argument. All right, and I'll just give it to you in a again in a very simple case. So we start once again with the source, which has two states and carries out this computation. I'm carrying now only, as I said in the slide before, only about the single computation case. Here's a point where I'll wave hands. It can be carried forward to the case of multiple computations. You know, Oron, in your book, you raised that question. I'm not going to go into it, but I think it can be done. Okay, and so here's our putative computer, our ROC, and it has, in this case, 6 possible states, and in the appropriate confined time scale, it goes through 5, goes through these transitions of one state to another 4 times, 5 different states. All right. Now, we know that this is okay because a rock does have an internal structure. It has atoms, has molecules. They interact with each other. And so this isn't a static object. There's no problem with viewing this as having states. There's no problem with viewing this as having states which are causally related one to each other. That's, Putnam thinks you need to heat it in order to get it to move. But it's really being very active in there right now. Okay. But now what we do, this is clearly not in homomorphic relation to the source. But what we do is we relabel the states. We put them into 2 groups. Okay, I've had them, I've colored them red and blue. Okay, and then we define a new notion, which I'll call G state, for gerrymandered states, that in fact lumps together Q1, Q3, and Q5, and lumps together Q2, Q4, and Q6, like talking about worth with numbers. Okay, and we will say that the rock is in G state 1 if it's in one of these 3, and in G state 2 if it's in one of the blue states. And now we can do our mapping. All right, and lo and behold, our homomorphism is in fact established. This moves in exactly the right homomorphic way. Nothing new to that. Okay, we've all seen that. Now, of course, G state isn't quite what we ordinarily mean by state, but so much the worse for what we ordinarily mean. Given a computation, the homomorphism, we can create that homomorphism, and it's there. And this is what I call the pernicious indeterminacy. Given a computation or abstract automaton, you cannot specify any determinate class of physical systems that implement that or realize it, short of the trivial class of all physical systems, or almost all, but there are no monadic Leibnizian monads here. So everybody has parts, and all those parts are always in causal interaction. The literature is replete with fixes, with solutions to this. Sometimes we require that the target mimic the architecture, the inner ordering of the states and of the transitions, step-by-step progress. But I think the two main ones are the causal and the honest mapping. Okay, we could require that our algorithm, that our homomorphism maps transitions into transitions that are causally sensitive to the environment. Slight perturbations in the environment of this rock could well cause it to go into different states after the initial state, and that would destroy our homomorphism. And the second sort of fix is that the mapping has to be honest. I think, Jack, that's your original term, okay? And what it means is that there's no hanky-panky. There's no gerrymandering in this case, as in this case. No vicious relabeling. So for the moment, let us remain untroubled by this pernicious indeterminacy. And let me briefly remind you of the benign or even beneficial indeterminacy. Okay, and this rests on what we've called, or what Aron called, simultaneous realization. All right, one target, okay, parsed differently, with therefore distinct homomorphisms according to how the raw data might be parsed. And here again, our well-known example. This I've actually taken directly from Aron's book, so as to really be indebted. That we have a machine that comes from two inputs, which could be high, medium, or low voltage, and the outputs are determined accordingly by the combinations. And we know that if we lump or combine the medium and low together, we will get a table of outputs, which gives us ZOR. And if we combine the medium with the high outputs, we get a table which gives us OR, inclusive OR. Okay. So there is a raw indeterminacy here as to what formalism the target is implementing. And that's the situation. Okay. That's what there is. But as Jack has been insisting all through this conference, this is a fruitful indeterminacy. The question isn't to get rid of it. The question is how to harness it. And in the case that's come up most often here, it invites or requires us to make use in our general terms, our general theory of a semantic term. Okay, this is Aron and Jens and others have argued for this, that in lumping the medium one way or the other, we are attributing content in order to know what the target is computing, in order to individuate the computation. And that parsing is a semantic interpretation. It attributes content. Indeed, for Aron and Jens, the semantic requirement goes even further. It's not enough simply semantically to disarm the two source, one target indeterminacy. You have to give a semantic gloss to that target itself. This is particularly relevant in when the target is part of the cognitive process. And Aron's equally famous example from computational neuroscience is the oculomotor integrator. The eye follows a moving object, and the process in fact involves mathematical integration of inputs. And so our target system must model that integration. In Aron's analysis, there are two pertinent activities going on in that modeling. He calls them mirroring and representing. I'm not going to go into them now. I'll simply point out that here too, there are morphisms involved between systems, which we now comfortably take to be faithful implementers. Okay, in my terms, these explanations are multiply extrinsic. Okay. Trouble in paradise. Let's go back to implementation. We saved it from the pernicious indeterminacy in two ways: a causal, or more generally, a modal constraint on the way the target components are grouped, or we can simply demand an honest morphism. And I want to look at those in order. First, causal or modal sensitivity is supposed to block the triviality because the particular gerrymandering doesn't take into account the different transitions, that would occur with a slight change in the environment. Okay. What we want to say is that whenever the rock or the state is in state Q1, it will move to Q2. We want that to be a necessary conditional. All right. So here's a reminder of what it means to say that that is a necessary conditional. This is a general modal model structure. And we can say that a particular order of transitions of states from one to another is necessary if, when we consider the relevant and close causally possible worlds, it will still maintain that order. All right, that's what it means to say that the move across here is necessary. It's causally determined. All right, it has to maintain that order. And that's simply not true for the rock. Okay. Some perturbation might move the rock or change the internal configuration of the rock in such a way that the order that it actually carries out, okay, in the time frame that we discussed, is no longer preserved. And it could be not preserved in different ways according to the laws of physics, according to what happens. Okay, here once again, I've renamed the states by T's, for target, to say that, this T1, T2, T3, T4, T5 corresponds to Q1, Q4, Q3, Q2 to Q5. That's the way, it actually happened, but it could have happened in different ways. All right. And so this order is not necessary. It's not causally robust, or put it in terms of this relabeling, this order is not causally robust. That's what we mean when we require that a set of transitions be causally robust or causally sensitive. Well, nothing requires that I give these states exactly the same T name in each of the possible situations, in each of the possible words. I could rename them. And I could rename them according to world. All right, and so that in Q1 they name what they should name. Okay, if I went back here. Okay, whoops. All right, I could rename these so that what? So that in fact the order T1, T2, T4, T5 is preserved in each one of the worlds. I can do this relabeling, okay, and if I do, lo and behold, our actual order becomes a necessary order. This is not a fancy trick. This is simply implementing the notion that Carnap introduced of an individual concept. An individual concept in a modal concept in a modal context is something that picks out particular things in different worlds. And so the individual concept T1, okay, picks out, or T2 picks out Q5 here, Q6 there, Q4 there. Okay, that's fairly standard modal logic. But with that renaming, okay, you find that something that was causally not sensitive suddenly comes out causally sensitive. There is no comfort in modality. It could get worse, and here's a place where I'll simply wave my hands. This example is what I call a respectful example. Okay, it's respectful of causal necessity and possibility. Okay, the arrows go to physically possible situations. But I can play out this game more outrageously and gerrymander so that even causally impossible situations get to be causally possible. The trick is, to use Jack's term, Oroning at the level of how we group possible worlds. And we do that and then making consequent changes to the to what's called the accessibility relation. And indeed, what it comes out is that suppose, you know, we have a state Q7 in which a piece of the rock moves a distance of 2 light seconds in a time of 1 second, something physically impossible. We can gerrymander so that even a transition that includes that can come out physically possible, or necessary at any rate. And so there is no comfort in causality either. Well, what about the other strategy? What about honest mappings? That's very nice. You know, no hanky-panky, no subversive relabeling, no insidious gerrymandering, no slitzing or Oroning in a wrong way. And we would be home. But can you be sure that you have one? Consider the case of numbers. Well, given a notation for numbers, it's simply undecidable whether your notation is actually referring to the natural numbers. As Bertrand Russell pointed out 100 and something years ago, you can't rule out models in which you're referring to the even numbers, okay? Or to multiples of 7, or to multiples of 131, okay? Now, for Nahum, that would be fine, because he doesn't care up to isomorphism, but I expect that most of us do. And that's not what we think we're talking about when we're talking about the natural numbers. And so we can't be sure in our ordinary talk about the natural numbers, which of these models might be we'd be referring to. But it gets even worse. It turns out that it can be undecidable whether your notation is actually referring to a non-isomorphic, non-standard model of the numbers, one in which there is a number that is infinitely distant from our ordinary natural numbers, okay, n star, and it has all of its predecessors and all of its successors. And so you can't tell whether your notation is ruling out a model like that. Now, I have a handout, which I haven't handed out, because I didn't want it to distract you. But in that, I've worked out exactly how such notations might work and shown not only that it could be undecidable, that you actually have the Turing hierarchy of undecidability for such notations. Okay. So you might want honest mappings, but it seems you can never be sure you have one. It's scarce comfort there either. Now, what's going on here is simply that extrinsic accounts involve mappings from systems to systems, from symbols to their references. Now, maybe as Andre suggested yesterday, that those mappings simply exist. I don't know. And frankly, that's not the point. The bottom line is that once you open the door to mappings, you have no way to keep those out. You bring in the deviant, the gerrymandered. Once you open the door, you can't hide from the bad indeterminacy. The very machinery that yields the benign beneficial indeterminacy, the machinery of morphisms, unavoidably yields its pernicious cousin. Okay, that's the first horn of the dilemma. Okay, let's try go for intrinsic accounts. All right, the examples, sometimes one wants to define the machine now simply in terms of its architecture, maybe its step-by-step nature, Cummins, account. Maybe more prominently, we use mechanistic accounts with, we require a rule-like clockwork mechanism, and we also have this requirement of median independence so it can be generalized. And accounts like these should avoid the first horn, should avoid the inevitable pernicious indeterminacy, because by their nature, they do not invoke a morphism from something outside the physical system in question. But there are two problems. The first problem is that just giving that sort of description, as we've heard and seen and read, just gets too much. Okay, a stomach can be described in these mechanistic terms, and it's all the stomach's activity is rule governed. It can be stated in a sufficiently general way. I actually like to look at this objection historically. This, for Philippos, constructing curves, as we've heard just in the last talk, is a form of algorithmic mechanistic behavior. The original instruments, the instruments that work in Euclid, the Platonic instruments, the compass and straight edge, are the earliest approach, the earliest suggestion for an architecture of a machine. Okay, a machine is made up of these instruments and it's used in the following rule-like way. Well, the fact is, for a long time that went going, though even already in Greek times, there were some questions about it. Descartes extended that. He made a machine that is different in order to get a larger set of constructible curves. All right. And he gave an account, a mechanistic description of the criterion for admitting a device like his. It can be conceived of as described by continuous motion or several successive motions, each motion being completely determined by those which precede. Clockwork, rule-like, mechanistic. Okay. He ran into a problem, the stomach problem. This description admitted too much. Just this description allows the construction of curves. He gives the example of the spiral, the quadratrix, and there are similar curves that should not be admitted. However, there are processes, not the Mesolab, but there are processes by which we can construct these curves. Archimedes already gave such processes. And so what does he do? He gives a constraint. All right, the constraint is that, I won't go through it, but it's an epistemic constraint. The steps have to be the sorts of steps that an ordinary human can grasp and hold together, and those other curves don't satisfy that constraint. All right, and so he added a constraint to the mechanistic. Nowadays, we don't generally use, well, Aron particularly doesn't like to use epistemic constraints on the mechanism. And so I'll talk about or mention teleology is often the constraint that's used. The machine has to be satisfying a particular purpose, okay? It has to be goal-oriented. and you need to have the right goal. Okay, stomachs don't compute. They have their goal, but it's not ours. There are refinements, but the thing I want to mention is whether your constraint is epistemic or teleological, it is essentially extrinsic. Okay, it must be mapped from a standard that is not itself part of the apparent mechanical description. And indeed, the mapping is modal. Applying it, you stand before an array describing the activity or possible inputs and outputs, okay? And you deem some of these to be acceptable, some not. Okay. And therefore they give, some give acceptable worlds, some give unacceptable worlds. But the bottom line is you're back into mapping, you're back into the extrinsic, you're back into all of those elements. And that's our dilemma. Take the extrinsic route, you've got trouble. Take the intrinsic route, you're either too weak or you're back at the extrinsic. All right. Well, where does that leave us? Here's a stab at a solution. I'll start with a historical point. It's one that comes from my conversation with Oron. Putnam produced his trivialization argument at the time he was developing his so-called model theoretic argument in metaphysics. It was his anti-realistic period. He wanted to refute metaphysical realism, the view that it's possible that our best scientific theory is simply wrong. It's possible that the real world is entirely different from what our theory says, that there is a right model of our language, which is different from the one that our theory claims. And so he showed that you can reinterpret the terms of our language so that it's now describing the right model. There's no sense, he said, to metaphysical realism. That's the background of the gerrymandering and relabeling that goes into the triviality argument. Putnam was very much influenced by the existence of non-standard models, okay, of number theory. Model theory from the time of Lowenheim and Skolem showed that a sufficiently rich language and sufficiently rich system can't avoid non-standard models. And any language that is about computing will be sufficiently rich. That's what's going on. And even in a system whose models preserve cardinality, you can only get it up to isomorphism. That, I think, is the deep underlying phenomenon here. The point is, look at the source, the target, the morphism in the model theoretic framework, and you can't avoid non-standard models, even in complete theories. Okay, that's the beginning, I think, of the solution for our conundrum. And I've got a page plus, so I'm good. Okay. Some people like to say we should think of ourselves as living in the standard model. Well, I'm not sure exactly what that means. Does it mean that we don't allow ourselves to think about that distant number that may be out there? Restrictions on what you think aren't really very practical. But restrictions on what tools you use and where you project, and when your project is like ours intellectually, then what you say, those can be more to the point. I want to distinguish between the projects of logic and metasemantics from the enterprise of empirical science and from our project of defining computation. Model theory is interested in the abstract relation of uninterpreted language to structure in order to establish criteria of validity and to characterize mathematical theories. Model theory strips both the source and the target to their set theoretic skeletons. Metasemantics is interested in metaphysical questions about how our language tacks on to the world. It applies to natural and scientific discourse, but views language and its interpretations as reciprocally alien domains in which the target gives meaning to the source. In both cases, gerrymandering is actually their proprietary tool. It's not simply formal syntax or the idea of reference or representation or mapping that opens the door to gerrymandering. It's the alienation and the stripping that make it possible. In the broadest sense, perhaps too broad, we can say that we do not share those goals characterizing mathematical theories, connecting language to the world. And so gerrymandering and relabeling are not our natural tools. Our language comes interpreted. We don't impose an interpretation on it. And we have our own tools and methods and assumptions. This can be viewed as saying, know where you stand. In our bailiwick, we know what we mean by a mapping and a system. We understand our language. To be sure, there are terms like computability that we are trying to define, but we do not speak in an otherwise uninterpreted language. And I might point out simply historically that Frege and Tarski, okay, did not think that their formal languages were necessarily uninterpreted, at least Tarski early in his work. Okay. So we might want to say that the maleficent labeling of triviality and modal reinterpretation are not natural tools for us. They're imported from different enterprises, a bad crossing professional lines. So the point is not relatively to labeling schemes, it's knowing our goals and the tools appropriate to them. In particular, visual system correspondence is an empirical and not a metasemantical hypothesis. It's studied with the appropriate methods. We, of course, use mathematics and we refer to it, but we don't do it, okay? The possibility that a system is performing integration is not a mathematical proposition, okay? Now, Stewart gave, okay, just that. All right. Stewart suggested that our notations should have a sort of buck stopping aspect. I want to go more general for a moment and adopt Quine's phrase and simply say we acquiesce to our language and our language comes interpreted. But it's not merely that we acquiesce to our language, okay? As I said to our own, we know what we're talking about. It's that we recognize our tools and we do not apply the wrong ones. We're tempted to go set theoretic and appeal to model theory because we talk of morphisms, but we mustn't. Does that mean that there's no place for the developments from multiple realization and OR gates, etc.? They come from duality and generality, not from gerrymandering. Does this stop triviality argument? Yes. Does it open the door to honest representations? I don't know. In general, where do we draw the line between our staying within our bailiwick and importing outside notions? That's more a research proposal than an answer. And I guess that's where I'll stop. I left out metaphysical speculation, but that's belongs in a different context. All right, are you doing it or am I?
Oh, whatever you prefer.
You just pointed to a wrong.
Yeah,
Okay.
wait. Oh, wait, let's go.
I was just wondering, you think that it's some like you said, can actually be used as kind of an argument in favor of the semantic view, because it seems that the semantic view, as I understand it, aims to solve what you call benign indeterminacy by fixing the labeling, and that would also solve kind of move to the unwanted indeterminacy. Can't change it everywhere.
So, as John Kennedy said, let me say this about that.
Can you repeat the question, please?
I'm sorry. The question was, does what I've suggested open the door to the semantic interpretation? Because I'm making something like a semantic move, and I'm saying that we accede to our language. And my view is that no, it opens the door, but it doesn't bring it in. I'm suggesting something at the level of the language in which we use to carry out the semantic interpretation, and the language which we would use to oppose the semantic interpretation. Both sides know what they're talking about. Both sides know that what they mean by a raw indeterminacy, a simultaneous implementation. Okay, and both sides within their within our framework are giving are giving arguments for and against this. In a sense, my suggestion is medicine. Okay, it's saying don't use metasemantics. Or don't use, the famous metasemantics. Not that there's anything wrong with it. Okay, I have to admit that I have, when nobody's looking, engaged in it. I've even published, but I don't wear that hat here. And what I'm suggesting is that that hat, okay, is inappropriate here. But again, where do we draw the line? All right. We could be inspired by, I have no idea whether Aron was inspired by the triviality argument to come up with the argument for this simultaneous implementation. But just like the people living in the if you could, in the standard model, and knowing that there could be a non-standard model out there, and refrain from doing what it takes to get to it, but could be inspired and use techniques that are translatable into the language of arithmetic without non-standard model, the ordinary language of arithmetic, use some tricks. Okay, one could say even that's exactly what Gödel did. But stay within, but he was very careful to stay within the bailiwick that he had set out for himself. And so it opens the door, but it opens the door to the other side as well.
Yeah. So thank you very much. And so my question is really about the implications of your suggestion, because okay, you talked about physical computation, and probably most of the people in the world who are interested in the problem are in this room right now. But the notion of implementation is also very central in computer science in general, and not just between abstract and physical, but also between different levels within computer science, like algorithms and programs, etc., etc. So, and it seems that the problems that we talked about here are also, I mean, we use basically the same notion of implementation. So my question to you is, what are implications of your suggestion to computer science in general?
My initial reaction to that question is that what I said now for a study like ours, okay, holds no less for formal studies. It holds within mathematics as well. Now within mathematics, we know that we are inspired by other areas of mathematics, assuming that computer science now is a field of mathematics. And we know that there is a great deal of cross-fertilization. Okay, but when we do the cross-fertilization, we have to be very careful, okay, that we don't generate paradoxes. Now, triviality arguments aren't paradoxes, but crossing the line in a technical technical field will give you paradoxes. And so if, computer science is not a branch of set theory. And computer science, only in certain areas is a branch of abstract model theory. It actually works the other way around. Model theory is computational model theory, which can take ideas from computer science. Okay, but in each and every one of those cases, and these are arguments, that I have in the philosophy of mathematics, mathematical projects, come with certain commitments to appropriate and inappropriate methods. And when we introduce inappropriate methods, if we're not careful, we will in fact get paradoxes. Okay, whether the paradoxes are inconsistencies or whether the paradoxes are monsters, we need to be careful about that. The cases that I'm familiar with most is category theory. takes a lot of material from algebraic geometry, but, but generalizes it. But if it's not careful, okay, it will run into the set theoretic paradoxes. And so when one does category theory, one on the side does the bookkeeping to make sure that we haven't, that we're dealing with proper classes, we're dealing with proper classes that are definable. We're not crossing the line and simply saying, okay, this way of thinking is unbridled. And so, my quick answer, to your question would be that I would apply the same sort of constraints to mathematical fields.
Mayor?
Actually, I mean, I just want to see that I understood you. I think that, even here, this is a little bit confusing to me because Putnam's model theoretic argument appears here on the slide, which is supposed to give a way out.
No, that's the historical background. That's just the historical background.
So, okay.
It's explaining how I parse the problem in order to get to the way out.
So, this is a little bit of a follow-up on the risk question, but in the other direction, it seems to me that, the direction in which we say, look, let's give up, let's say, respond to the sort of set theoretic paradox, the model theoretic arguments, and so on, by just saying that we know what we are talking about, so that the language comes already interpreted. I think I'm not sure I understand what it means, because
That's
we have to give up. As Quine actually, I think Quine's response was we have to give up on the notion of purpose.
no. Okay, I'm sorry.
This is at least that I saw it in a quotation that's given by Putnam in representation of reality, and it seems that if we give up, so if we go in this direction, then the whole idea of semantics, I think, is in danger, serious. So, I don't know what people are doing in the neighborhood and so on, but.
So I'm absolutely not, suggesting that we give up the notion of reference. I'm absolutely not suggesting that we give up the notion of labeling. I'm absolutely not suggesting that we stop talking about implementation. And nothing, in fact, I'm doing the opposite of that. I'm suggesting, though, that we do not strip down the notion of reference to the abstract mapping from an uninterpreted language to a uninterpreted set or to a gerrymandered set. Okay, that when we talk about when we talk about a computer physical system implementing, an abstract system, we do not reinterpret our understanding of what the physical system is. We do not take it as simply a collection of uninterpreted counters or of discrete physical objects. Okay, that's a move which is not necessary for our activity, and that's a move which you can do it, all right. And then when you see the consequences, you look back and say, where did I go wrong? Which aspect? And so when I asked where draw the line, the methodology to know where draw the line is when you come up with something which is ultimately counterintuitive. Okay, some suggestions have been live with it. I'm suggesting look back at the popcorn trail of how you got to it and see whether at some point you introduced notions that really have no other application in this in this field of research. That's what I'm suggesting.
We have to end. Let's thank our speaker very much.
Thank you.
So guys, on this positive note, we're done. Or you want to say any words?
Well, no, thank you very much for coming. I hope you enjoyed. And yeah, and I want to thank really the team of the Institute. They are not here, but without them, we couldn't have this wonderful event.
Thank you all for coming.
Yeah.